All right, young kids, we're going to talk about some stuff today. Here we go. The first thing is going to be distance in the XY plane. We're going to work our way up from distance to area to volume. Okay? All based on the same foundations here, really. So, pay attention, write this down, ask questions if you got them. Here we go. The distance we worry about in a Calc 1 class is either, so I know there's a distance formula. We're not going to worry about that crap. Okay? We're going to be doing vertical distance or horizontal distance. Let's start with vertical distance. Okay? All right. If I were to make up two fantastic points, like one here at 3,8 and one here at 3,1, and I asked you, Kevin, how far apart are those 2 points? You would tell me. What? You sure would. 7. Okay? And you know what math we did there? 8 minus 1, 7. That's so easy, right? We're going to exploit that a little bit. Here we go. I'm going to move over some. Everybody with me still? I want you to notice. I said, everyone with me? Yes. Are we good? Come on. Yes. Keep up. Ready? Let's say we had that same point, 3,8, but we gave it a new friend, like 3, -4. How far apart are those points, Jeff? 12. It doesn't matter if one's positive and one's negative. You find the distance the same way. 12. They could both be negative, but we do the same dumb thing. Okay? Now, we don't want to deal with points. Those are like, stationary things. Let's think maybe, what if we had some cool function up here, which I'm going to give it a really cool name, f of x. Okay? I know, right? And we had this line down here, like y equals 1, I guess. I don't know. Well, how would I find the distance between any point on f of x straight down to that line? What do you think I would do?
I don't know.
For instance, the distance from here to here, or the distance from here to here, or the distance from here to here. No, we're way too complicated here. F of x minus 1. That is it. That's the distance. Now, in the previous examples, we could find the exact distance because we knew what 2 points we're dealing with. Here, the distance in question is dependent upon x. It depends on what x value I chose to find the distance between. Does that make sense? Yes. And lastly, if I had, again, another f of x cool curve, and then down here, I had like another curve like g of x, how far apart are these 2 curves? F of x minus g of x. Now, here's what you keep in mind. The distance is dependent upon x. There's x's in there. But we're not subtracting x values, we're subtracting y values. I need the x value to know what the y value is, and then we subtract that. Make sense? So in general, to find vertical distance in the xy plane, all we are ever doing is the top thing minus the bottom thing. Easy enough? And for our purposes here, there will always be some y value minus some other y value. Okay? Top minus bottom. Great. Horizontal, very similar. Let's talk about that. Are we all good? If we want to talk about horizontal distance, let's see. Well, now I got to choose points like 8, 5, and I don't know, -2, 5. How far apart are those points, Ashan? 10! Thank you, sir. They are 10 apart. Hello. The distance between these points is 8 minus -2. What's up? Thank you so much. Jill and Zion. There you go. So, what if we had this point over here and I called it like AB, and I had a point over here which I called CB. Notice that they both have b's in their y values because of the same y, the same height up there. What's that going to be, Bennett? What's the distance between those 2 points?
C minus A.
Ooh, no, sir. A minus C, yeah. Keep that. So, when you got numbers, it's easy to tell you're going to do right minus left, right? Big minus small, that's distance, always positive. Once you start throwing variables in there, you got to think for a second, but it's always right minus left. So let's write that up here. Horizontal distance is right minus left. But that means we're not subtracting the y values, we are subtracting the x values. So let's take a look at what that might look like if we had like a curve of some kind. Okay? Let's say we had a line back here at like x equals -2. That's fun. And I had some curve over here like that. Okay? Does it make sense? The distance between the line and the curve are changing? Cool. But now the distance between them is not dependent upon the x value. It's dependent upon the y value. So the distance between these two things is not going to be f of x minus -2. It's going to be f of y minus -2. Okay? I'm going to say that again. Because the distance now depends on the y value that I'm at, I need it to be an x value that I'm subtracting. So if f of x is a y value, f of y is an x value. Okay? Let me give you like a concrete example. I'll give you a real curve and we'll talk about the distance between these things, okay? So, let's say we had, I don't know, the square root of x. Nope. X squared. Y is x squared. And we had over here the line x equals 10. Okay? If I want to find the distance between those things for any y value, I hope it makes sense. We're doing right minus left, right? What's on the right-hand side of that? No matter where I draw my line between them, what's on the right-hand side? 10. What's on the left-hand side? X squared. But I can't say 10 minus x squared, and here's why. If I said 10, again, this is wrong. This is sad face. Don't do this. Okay? It's not 10 minus x squared because if I said this value here was 2, well, how far apart should 10 and 2 be? 8. But if I do 10 minus x squared, I'm going to get 4 in there. That doesn't make any sense. That's the y value. The y value there would be 4. I don't want that. I need to subtract off what the x value is. So what you do is, it's 10 minus, you solve this for x. I need to subtract the x value dependent upon the y value. So it's not 10 minus x squared. It's 10 minus the square root of y. They're the same. Does everybody see they're the same curve? One is defined dependent on x, and one's defined dependent on y. We need the one that's dependent upon y in this particular case.
Why can't we just say 10 minus x?
Because the x value is changing, I'm going to show you why. You're right, it is 10 minus x, but I'm going to specify that x is stuck on that curve, and that's what root y does. It forces it to be on that curve. If you do 10 minus x, it could be anywhere. Does that make sense? It'll make more sense when we're looking in terms of areas and volumes, all right? Okay. I was going to say something else. I forget. Oh, you know how we got positive, negative root y here? That's because there's really two pieces to this. Negative y is over here. So if I had to go all the way back to that side, it would be 10 minus negative root y. Okay? We looked at that last year with conic sections. I'm not going to get too much into it right now. But it suffices for us to be able to find distances by subtracting. Either top minus bottom or right minus left. Everybody's with me on that? Excellent. Let's talk about areas then. We're going to use that idea there to find areas. Now we've already been finding areas in the xy plane. Okay? For our purposes, area you can always think of, with calculus-wise for us, as a length or a height or a width. I'm going to write length, but some distance. Okay? Distance in the xy plane multiplied by an infinitely small, I don't know, distance, like width. Yeah, let's say width, okay? Again, these are interchangeable things here. What do we get when we do length times width? What's that find? Area of a rectangle. We're always using rectangles. Okay? And that's why our angles look the way they do. Now, that's just one rectangle. We're going to integrate that. That finds an area. Okay? I'm going to, what's up? Well, area of any shape. So let's break this down. Let's say, stick with me. Let's stick with x squared again. Out to 3. So I'm saying y equals x squared. Everybody with me? Let's say I want to find the area in here. Now, before today, you should have been able to do this already. Okay? It's just the integral of x squared from 0 to 3. That's what the integral finds, right? Area. Okay? But what we're really doing there, and I've walked you through this before, what we're really doing there is we're dropping, I'm going to erase these little dashed lines in here. Let me change up colors too. Let's get fancy. What's your favorite color?
Red.
Good.
Purple.
Red.
Oh, wait, it is red.
Blue it is. Okay.
I don't think anyone said that.
I heard blue back there. That's how I am when I do my improv. It's good. Okay. Sounds racist. Okay. Doesn't make sense. There's a rectangle in there. And although I am drawing, I probably shouldn't say that on put it on YouTube. Although I'm going to say, I have to draw a thickness because I'm drawing this rectangle, right? But how many rectangles could I really draw between 0 and 3 in here?
A million.
Infinitely many, which means their thickness is actually infinitely small. Okay? So, look, does it make sense that now where I draw these rectangles, what's the top of them always? X squared, and the bottom is 0. So the distance there is always x squared minus 0. Now, we don't usually write minus 0, but let's write it out for right now. The distance, the height, if you will, of every single one of those rectangles is x squared minus 0. Easy enough? What's the thickness? That's this length right here, by the way. What's the infinitely small thickness of each one of those rectangles? Since we're crushing it, it's an infinitely small change in x, which is dx. I know, right? This is why all the physics stuff works.
Hey, physics.
That right there is the area of any one of those rectangles. We don't want one rectangle. We want all the rectangles summed up. So we put a big old S out there. Look at that big old S. Okay?
Samsung.
And then we tell it, hey, integrate on all the rectangles from x equals 0 to x equals 3. And I'm using x values because x at the end here, dx, denotes the variable I have to use. Okay? So I'm going from 0 to 3. I've got x squared in there. It all checks out. Make sense? And just for fun, let's do it. The integral of x squared, again, this is asked for the area, but we know that the area under a curve is the same exact value as the change in its antiderivative. So rather than calculating the area, which is hard to do for a parabola or any kind of weird shape, we find the antiderivative, which is also kind of hard sometimes, okay? But we find the antiderivative and we find how much it changed. So the antiderivative of x squared is 1/3 x cubed. And does it make sense? That's just one antiderivative. Another antiderivative could be 1/3 x cubed plus 10, or 1/3 x cubed plus 100, or 1/3 x cubed minus 1,000,000. Those are all antiderivatives, okay? But because we only care about the change in them, we don't care about the constant at the end. Because it doesn't affect change. It affects the actual value, but not the change. I want to know what that is doing as x goes from 0 to 3. I want to know how much it changed. So I plug 3 in, and when I drop a 3 into there, I get 9. So when x is 3, that antiderivative is 9. And then I plug in a 0, and I get 0. So it turns out that on the interval from 0 to 3, the antiderivative changes 9. So the area under our original thing, x squared, must also be 9. Simple enough? That is not new at all, right? Hopefully that clears everything up for us here. Now, do you notice how we're always using these vertical rectangles? That's what we've been using this whole time with x's, okay? And there's really no reason for us to be using. It's only because we use f of x all the time. There's really no reason why I can't take that same shape and fill it up with horizontal rectangles. Does that make sense? Woo! Look at them all. I can draw them all in there. Great. There's infinitely many horizontal rectangles in there. But now, what's the height of each one of those rectangles? It's infinitely small change in what variable? Y. So it's dy. And what's the width of each one? What's on the right-hand side of every one of these? 3. And what's on the left-hand side of every one of them? But we can't use x's because we got the dumb dy there. Well, it's not plus or minus, it's just 1. And because, so you're right, solving it would give us plus or minus, but since we're on the positive side, see all the x values are positive there? Positive root y. If we had the other side of the parabola, it would be negative root y. Are we good? It makes sense? Yes? Guys, this is also why the integral of velocity finds distance. It's how fast you're moving times an infinitely small time, plus how fast you move times how much time went by, plus how, okay? It's why springs, forces, and work done are all done like this, because work is force times the infinitely small distance that it's applied on. If you have a constant force, then it's just that force times distance, right?
Yeah.
But if the force is changing, you got to chop it up into small intervals, which is exactly what we're doing. Okay? That's all I know. Okay, good. Makes sense? What's the area in there? What's the area of one of those rectangles? 3 minus root y times dy. But I don't want the area of one of them. I want the area of all of them added up. Great. And then I tell my stupid integral sign there, not stupid, my friendly integral sign, to add up all the rectangles from when y starts at 0 and goes all the way up to 9. Not 3, 9. Good. And if math is not one big lie, this integral should equal 9. Because the last integral equaled 9, and they're both finding the same area. True? So let's just do it real quick. The antiderivative is 3y minus, that's y to the 1/2 power, so it becomes y to the 3/2 power times 2/3. I don't know how much that changed from 0 to 9. You ready? When we plug in 9, we get 27 minus 9 to the 3/2 means take the square root, that's 3, cube it, that's 27, and multiply it by 2/3. That's 18. Minus, plug in 0, 0. And guess what that is? Holy goodness gracious, it's 9.
Whoa.
I know, right?
That's like center of mass.
Okay. Center of mass is when you add up all the weights like we just did, then you got to divide. We'll get into it later on. Well, we won't, but I'll tell you after school. Okay, whatever. Okay? Yo, guys. Yeah, it's not going to center of mass. If you have a distribution, like weight distribution function, you can throw all this crap in there. We're not going to get into that. What was I going to say to you? Oh, key thing here, kids, which is not crazy important, but we just did the same question 2 ways. Okay? It turns out that sometimes when you can do a question in 2 or 3 different ways, one of them is substantially easier than the others. In this case, they're both about the same, but it makes sense. The first one's easier, right? Not by a ton. That's all the same, like math. Okay? But it's a little bit easier. So that happens a lot in math. Sometimes one way to solve a problem is to convert it to a totally different system and answer it there. Okay? What's up?
Is there ever going to be a time when, like, a test or something where it tells us to use, to derive with respect to y?
I don't think they will tell you which one to use, but sometimes they'll make it impossible for you to convert it. Because look, so in us converting from y equals to x equals, we're saying there has to be an inverse to that function, right? Well, not all functions have inverses, okay? And sometimes, like think about cosine. Like if we, and actually let's just do one more example here. Let's say we had a graph of cosine x, thusly. Can we handle that? And we also had x squared minus 4. So cosine x and y equals x squared minus 4. And let's say I'm just dying to know the area bounded by those graphs. So that's this weird shape here. Does that make sense? Okay. Well, we could try to put horizontal rectangles in there, left to right. But what's weird about that is if you do that, check out this rectangle here. What's the right-hand side of that rectangle? Cosine of x. What's the left-hand side of the rectangle? Cosine of x. So it doesn't I mean, they're different x values, but you can't, yeah, so here we have to use vertical. Unless we want to get super tricky with like inverse trig stuff, which I don't want to get into. Okay? But there's really no point in doing that. So we would use horizontal rectangles, okay? I'm sorry, vertical rectangles. Vertical rectangles. All right? Our rectangles are going to be, so something we got to pay attention to is that the top is always what function? No matter where I draw it in here, the top is always cosine, and the bottom is always x squared minus 4. So, every one of those rectangles has a height of cosine x minus x squared minus 4. Notice the use of parentheses. Okay? You're subtracting quantities here. So put a parenthesis around the big quantities. You can put them around cosine as well, but you don't really need them. Okay? How thick is every single one of those rectangles? Infinitely small, but we're going to call it dx, an infinitely tiny change in x. Remember, that dx is not, I know we've just been putting it there since we learned integrals, but it means something. So pay attention to the variables and what you're actually putting in here, because a super common mistakes kids will do is they'll use dx when it's really supposed to be dy, and then they got all the wrong functions and all the wrong values on their integrals. Pay attention to the variables, okay? And that's just one. I want to add them all up. So we integrate, but now I don't know where to integrate from. So if you have to find intersections, which is what we need right now, right? I need to know where those things intersect. You do, on a calculator, one of two things. Okay, so let's talk about finding intersections on a calculator. Do y'all got calculators? You can do this, or you can just pay attention to me. It really doesn't matter. To find intersections, what we really need to solve is this. Does that make sense? If we can do that by hand, we solve it by hand. We'll do one by hand in a second. Okay? If we can't do it by hand, or if we have a calculator anyway, then why not just use the dumb calculator? So in a calculator, you do one of two things. You either graph y1, y2, graph them both, and then use the intersect button. Right? That's the first way you can do it. Or, what I think is easier, but I don't care how you do it as long as you can do it, is take one minus the other, and instead of looking for intersections, look for the zeros or the intercepts. They're the same thing.
Does it matter which one you subtract?
Nope. So if I do x squared minus 4 minus cosine x, and you do cosine x minus x squared minus 4, we get the same exact zeros, except our graphs will be flipped over. Okay? Make sense? So on a calculator, I'm going to do this real quick. Now, what's important to note is that for the AP exam, your final answer has to be 3 places accurate. That's out to the thousandths, which means any number you use in the problem has to be accurate out like 6 or 7 places. Okay? So you got to find these intersections and write them out all the way. So we talked about how to store that. I'm going to show you again real quick. Let's make sure that I am in radians. I'm not. Cool. So I'm just going to do x squared minus 4 minus cosine x. And I like this better doing it this way simply because now I know what y value I'm looking for. I want to see where this thing hits 0. When you graph them both separately, you don't know what y value where they're going to hit each other. If you know what both functions look like, then you can set up a reasonable window. But sometimes the most common mistake or problem I hear kids have here is like, I don't see where they intersect because they can't find the right y. They can't find a good window. Now I know I'm just looking for the zeros of this dumb thing. So I always set my y to go from -1 to 1 because I don't care what the whole graph looks like. I just want to see where does it hit the x-axis. Okay? So my window is going to go from, again, x. I'm going to go -5 to 5. But if I don't see it in there, I'm going to go out further. Okay? And if I go out really far, I don't see it, then I'm going to zoom in real far on 0. Because sometimes like intersections like 0.001 is really hard to see. Rarely, but sometimes that happens. All right? But we're going to go -1 to 1. And I'm going to graph it. Oh, my x scale. So again, too, I like to set my x scale so that I can kind of see what the answer is going to be without having to do too much work. So I set it as 1. And then I'm going to graph it. And we should see one negative and one positive answer. Oh, there's 1. And there's another. And because I set my scale so nicely, I'm so good at this, I can see that they are close to 2, right? A little bit less than 2. Now, we got to find the exact value, but it gives you like a little bit more heads up about what's happening right now, okay, rather than just relying on the calculator completely. Everybody with me? Okay, now we're looking for a 0. So we hit second trace, we want the 0, that's 2. And you can move your cursor, or you can say look between these values. It looks like it's around -2. So I'm going to say look between -3, enter, -1, enter. And you can guess if you want or just hit enter again. And it gives me this number, -1.914021. Everybody got that? Okay. One benefit of doing it the other way, where you graph y1 and y2, is it will tell you the y value as well. Because as we just saw, sometimes you need to know what the y value of a point is. But if you do it this way and you get the x value, guess how you can find the y value? Plug it right into one of the functions. You should get the same thing for both of them. Okay? Now, something you can do here real quick is quit out of here right after this. And so we don't have to keep typing that number over and over again. Hit stow, which really means store. That's right above on. It's going to store the x value that we just found. And then hit alpha and pick a letter. I'm going to call it A. There you go. And now anytime I put in alpha A, I'm going to get that number. Make sense?
Wait, how did you copy the number from?
You just hit store and it takes it as your answer. You see how it says A and S? If you hit store, it just takes the last thing you typed in. Unless you type something in and then hit store, then it stores that thing. Also, if you store something else in A, it will overwrite this. Okay, it doesn't save it forever. It's just like a placeholder. Okay, on your paper, free response-wise, if I were you, I would do this. I would write, because a lot of times you got to use these values over and over again. So I'd write somewhere on my paper, A equals -1. What was it? 91401.
06.
Oh, okay, got it. Bam. And I know I didn't find B, but I happen to know that both these graphs are even, so it's symmetric. So it's positive 1.914, whatever. Make sense? And then in my integral, I'm just going to put A to B. A benefit of that is, again, is sometimes they make you use the same point multiple parts of a question. So if you call it A, now you have to keep writing it. You just write A. Make sense? As long as you write somewhere on the free response paper, you can just call A and B now. Simple enough? Okay. I'm going to do one more example, and then we'll talk about volume. Okay? There's a lot going on here. I'm recording this, so you can always come back to this if you need to. I've also got another video I'm going to put on Canvas. I'll put a link on there. I think I'm walking through like an AP question maybe. Okay? In case you guys get bored and need something good to watch. There's nothing good on Netflix right now. Okay?
Alter carbon.
Huh?
It's a matter of opinion.
Okay. Let's say, sometimes they don't give you a graph. Sometimes they just give you functions. So let's say, it'll be worded like this. Find the area of the region enclosed by, and they'll give you some functions. Y equals the square root of x minus 1. Y equals -x plus 7. And the x-axis, we'll say. Okay? Now this would be a non-calculator kind of question. So, and honestly, a lot of times College Board on these non-calculator questions, they'll give you a graph. Most of the time. Not all the time. Okay? But you should know what these look like. You know what root x looks like, right? Looks like a parabola sideways. The -1 is going to shift it 1 to the right. So that's going to be here. And it opens up like this. -x plus 7 is a line with a slope of -1 and a y-intercept of 7. And it has an x-intercept of 7 as well. So it hits down here, and it goes like this, and it hits up here at 7 too. Does that make sense? Do you see how those two curves by themselves do not close off a region? It's like a big X kind of. There's 4 regions there, right? Top, bottom, left, right. So depending on what other piece I give you, it closes it off. For instance, if I had said not the x-axis, if I had said n x equals 10, then there'd be a line out here at x equals 10, and we'd be looking at like that area over there. Okay, handle that? We're good? But we're not dealing with that area, so let me erase that dumb thing. Undo. Undo. Oh, really? One at a time? Okay, great. Okay, we're doing the x-axis, which is right here. So you see we got this like semi-triangle looking shape here, like a wedge of cheese or something, I don't know. Make sense?
Yep.
Okay. Now remember, to actually find area, you can choose vertical rectangles or horizontal rectangles, whichever one you think is going to be easier. I'm going to show you both real quick. Okay? if we had to do vertical rectangles, or we wanted to do, something you should always think about is if you draw your rectangle in different places, do you have the same bounds? For instance, if I draw, let me change colors again. If I draw a rectangle over here, it makes sense the thickness is dx. Once I decide on vertical rectangles, the thickness is going to be dx for all of them. Okay? But the height is what? The height of that one is root x minus 1. Minus 0, technically. Yeah? That's going to be true for all the rectangles up until right there. Once I cross that place, now so look, the rectangle I want has to go to right there, right? But if I use root x minus 1, it's going to go all the way up to here. We'll be finding too much area. I don't want it to go that high. Okay, the height of that rectangle is negative x plus 7. And again, technically it's minus 0 on both of these. If these things had a bottom that wasn't 0, we'd have to subtract that off. Make sense? So, just like we do with other composite shapes here, we got to do two different formulas for this, right? Two different integrals, really. My first integral is going to be the top minus the bottom. So it looks like that. You don't have to put minus 0, but that's what we're really doing. That's the height of every single one of those rectangles. And we're going to multiply by its thickness, dx. But those rectangles only go from, where do they start? What's that x value? 1. And they go until here. I need to find that x value. To find the intersection, you set them equal. I promise you, if you solve this out, you're going to square both sides. You can also just guess and check on this, really, but you get that. You move the x's over here, so you're going to get minus 15x plus 50. Everybody with me? I'm going a little quick. I'm just solving an equation. Square both sides, move everything one side, factor. That is a golden math fact. If you have to solve an equation and there's multiple x's, you can't get them together, you got to factor it or use a calculator. Okay? So we get x minus 5, x minus 10. And we get two answers, 5 and 10. Which one do we want? 5. Yeah, 10 is an extraneous solution. Cool? 10 is happening because if you were to draw the other side of this parabola, like down here, that line's going to hit it again at 10. But that's not even on our graph, so it doesn't matter. We're going to 5. That's going to find the first piece. And then I need to do the integral from 5 to 7 of negative x plus 7 minus 0, technically, right? Times dx. What's wrong? Does it make sense? This should be hopefully pretty clear, right? These are generally considered to be complicated questions here. There's a lot going on. But you think about little terms of rectangles, it's not too bad. Now, that was with vertical rectangles. With horizontal rectangles, it's a little bit easier. We only need to do one integral. So let me write that out, and then we're going to talk about volumes. All right? All right, good? Can I go? Okay. So just hang out. How about that weather?
Terrible.
So good. What do you mean? It's beautiful outside.
There's pollen everywhere.
Pollen everywhere. That's Mother Earth attacking you. What? It's also what? Oh, just pollen? Shouldn't have allergies, nerds. Huh?
When I left Detroit,
Like, I control that.
when I got run out,
Oh, man.
I guess I asked you
Okay. That was a bad lesson in distracting a whole class. Okay. So, if we were going to do horizontal rectangles, they would look something like this. True? Do you see that no matter, it looks harder because you're used to the vertical, but do you see that no matter where I draw that rectangle, what defines the right-hand side? Negative x plus 7, but because I know my thickness is going to be dy, right away, I know I need to solve for x. So x is negative y plus 7. Guys, that's not just because I switched them, it's if you solve for x, that's what it is. Is that okay?
Yeah.
And they're defined on the left-hand side by y equals root x minus 1, but that, for us, is going to be y squared plus 1. Easy peasy. Now, the area of every one of those rectangles is its thickness, its width, right? Which is negative y plus 7 minus y squared plus 1. That's how wide they all are, right? Times the height. But the height of every single one of those is dy. That's the area of one of the rectangles. We want to find all of them. So we add them all up from when y goes from 0 all the way up to
Intersection.
the intersection, which is when x was 5. And if x is 5, y is 2. Okay? And we can do that by hand. I'm not going to get into all that, but that's you don't have to do them both ways. You should not do them both ways. Okay? One way will suffice. I'm just showing you. What's up? Whichever one you like better. Okay? If it's a multiple choice thing though, and you see all the answers have dy's on them, then you might want to seriously consider horizontal rectangle. Okay?
Wait, can you explain about that again?
Yeah. So you see my rectangle, right? It's defined by this distance to here. So that's the right minus left, which is this piece right here. We multiply by how thick they are, but since I'm crushing it down, their thickness is all dy. And then I'm going to add them all up. I got to tell her what y is doing because y is my variable here. So y is going from 0, which is here, up to this point. But that was when x was 5. If you put 5 in there, you're going to get 2 out for y. Make sense?
And you put 5 in any of them?
Yeah, you should put 5 in the both and you should get 2. Because if you don't get 2 for both of them, something's wrong. Okay? All right. Let's talk about volume. There's an awful lot of math in one class. You're doing great. Some of you are so excited. Ian's sleeping. Liam's down for the count. This is good. Okay, oh, Gabby, I'm losing you. Excellent. Kids these days.
Back in my day.
Yep. Yo, remember I told you area was just a length times a super small width? Right? That's what we just did for every one of those. It's always rectangles. Volume can be thought like this.
Yes. Where?
Actually, before I even get into that, let's think about this. Imagine a deck of cards. You know what a deck of cards looks like?
Yeah.
Okay? Does it make sense that if I were to find the area of one face of the card, right, and multiply by how thick the whole deck is, that will be the volume of the entire deck of cards? Okay? Yeah. It's cross sections. Okay? That's the only kind of volumes we do in this class, is cross-sectional volumes. Meaning they all have the same shape, cross-section. Now, cards are all the same shape and exactly the same dimensions, right? But imagine cards that got slowly smaller as you went up and you stacked them. What shape would that make? They make a pyramid. But we could still find the volume of the pyramid by taking the area of each card. We'd have to have a function now for the area because it's changing, times how thick each one was. But since we're crushing them down, we'd call it like dy or something. And we'd add them all up. So volume is going to be an area equation, depending on the shape of the cross-section, times an infinitely small, what did I call it before? Like a width, we'll say, I guess. I don't know. That's going to be the volume of one of our little shapes. Okay? We want to add them all together, so we are going to integrate. All right? Let's do one super cool example. Let's say I knew that there was this shape. Let me see here if I can make this happen. Like that, and then down here. Something like that, okay? Let's call this top curve f of x, and let's call this bottom curve g of x. And let's just say this value here is 10. If I wanted to find the area of that region, does it make sense that I would simply do the integral of f minus g from 0 to 10 dx, right? Okay, but let's pretend that that's not just the area. Let's pretend that's the bottom of a shape, like a footprint. Okay? That's the footprint our shape would leave, but the shape itself is actually made up of a bunch of triangles. Okay? Triangles that are perpendicular to the x-axis, sticking out of my screen or the board here. So imagine this line right here. That represents the bottom of one of my triangles. Can you imagine what that shape might look like? Oh my gosh, like that one right there for our viewers at home. Let's see here. Kablow! Do you see that right there? Yeah? Uh-huh.
What is that?
Hey, look at all those triangles in there. You see that thing?
No.
What do you mean, no?
How do you determine the height of the triangle?
So. Sometimes they'll tell you the height is like 2. Now, these triangles don't have the same height the whole way through, right? You can see that. They're going up and down. Because these triangles are special triangles, okay? They are actually 45, 45, 90 triangles. They're isosceles right triangles. See, if I turn it like this, it's half a square. See that thing?
Yeah.
Can we make one?
It's half a square. It's also, yeah, you guys can make some. Okay, sure. That'll be fun. Okay? Here's the main point, gang. Ready? Look. Let's call this value up here A and this value down here B, right? What just happened? A, B. Sometimes OneNote doesn't like when I leave it and come back. Okay? It's like my dog. All right. Does it make sense that that length right there could be right here if I picked it up and I said this was A and this was B? Yes, if I took it turned sideways.
Sure. Yeah.
Sticking out of that is a triangle that looks like this.
Whoa.
Now, again, it's an isosceles right triangle, meaning this is a right angle up here, and these two are the same. So does it make sense that the further apart the curves are, the bigger that triangle has to be? Because they're all proportional. They're not the same triangles, but they're proportional. They're all 45, 45, 90, right? So the bigger the width of the base is, the taller the triangle goes up. But, hello again.
I'm sorry for interrupting. Can I really go back on some services?
Go ahead, Jillian. All right. Does it make sense, though, kids, that the volume, stick with me here, the volume of one of these things is 1/2 the base height. What does that find? The area of the triangle, and then we multiply it by how thick it is. How thick is the triangle?
dy.
No, what are we crushing?
dx.
We're crushing dx because they're all perpendicular to the x-axis. Okay? If they were perpendicular to the y-axis, that'd be a lot harder. Okay? That's the volume of one of them. I want to add them all up from
0 to 10.
0 to 10. What's the problem with this integral? What's it depend on? Well, we need it to depend on x because I got a dx at the end. I can't have a dumb b and an h in there. I got to get rid of them. Luckily, the base is exactly what I see in the xy plane. It's this length right here. How far apart are those two curves?
F of x minus g of x.
F of x minus g of x. That's super sweet. The 1/2 can go right out front. The base of the whole thing is f of x minus g of x. And then I need the height. Now, you're right. How do I find the height? The only way we can do this is if the height is based off of that base. Or they all have the same height or something like that. Well, it turns out, does it make sense that if you were to take a triangle like that and attach another one down here, guess what shape that makes? O square. And this is the diagonal of that square, true? So guess what this is? Half of the diagonal. Yes? Half the diagonal. So it turns out the height is just half the base. So the height is 1/2 f of x minus g of x dx. Now we're going to simplify this down a little. Everybody with me? Make sense? It's a half base height times its thickness. We're adding them all up. But we need it to be in terms of x. If they were perpendicular to the y-axis, we'd be in terms of y. We'd dy's. Okay? That would be a whole lot harder for this question. Now, let me show you something. The 1/2 and the 1/2 can both be brought out front. That's a 1/4. Cool. And then I have f minus g times f minus g. Guess what that is? F minus g squared. You ready? I'm just going to show you one other way to interpret this. That's the volume right there. You put it in as an integral, you integrate it, okay? Stay with me here. If this 1/4 wasn't there, pretend the 1/4 is in there. If I just took the base and squared it, what's that find the area of? A square, right? Side squared is a square. The reason why this is 1/4 of it is if you take a triangle like that, guess how much of a square it makes? 1/4 of the whole thing. Okay? I'm going to give you a formula sheet for all the shapes you're supposed to know. Okay, good talk.
Do you get that
No.